Today I want to discuss an issue related to the numerical stability of the algorithms that we have been discussing that has to do with how we compute the weights, the probabilities of the components, both in the EM algorithm and in the MCMC algorithm. So numerical stability is going to be the key topic of conversation. And if you remember, we've been computing quantities of the form BIK equals to some ZIK divided by the sum from L equals 1 to capital K of ZIL, where this ZIL in our algorithms looks something like omega sub K G of x sub I given theta sub K. So these quantities, we are sure that they are positive because this is a density and this is a number between 0 and 1. So we're computing these kind of ratios where we have a positive number divided by the sum of a bunch of positive numbers. When we have been doing this in the computer, if you remember our discussion of the EM algorithm and the MCMC algorithm, what we have been doing is we have been working in the logarithmic scale. The reason for that is that when you work with numbers that are very small, in particular if these z values are below the smallest number that the computer can represent using its finite precision, then those numbers are represented as 0 in the computer. And in that case, you end up trying to divide 0 by 0, which is clearly something that doesn't have an answer. So to avoid that kind of numerical issue that arises not because of the algorithm per se, but because of the fact that the computer has a finite representation, we are going to need to adjust the way we do the calculations. And actually, the adjustment is very simple. As I said, we're going to be working on the logarithmic scale. So what we're going to be doing is we're going to be using the fact that because the exponential and the logarithm are inverse functions, we can rewrite this expression up here as exp of the logarithm of zik divided by the sum from 1 to capital K of exp of the log of ZIL. So these two expressions are the same just because the exponential and the logarithm are inverse function to each other. And now that we have written things in this way, the other thing that we can do is we can multiply both the numerator and the denominator by the same quantity to rewrite this as exp minus b. And b can be any number that I want. Exp of zi of the logarithm of zik divided by the sum from L equals 1 to capital K exp log of ZIL. And the last step is just to basically combine these exponentials all together to rewrite this as the ratio of exp of the log of zik minus b divided by the sum from L equals 1 to K of exp log of ZIL minus b. Now, in other words, if we do the calculations of this quantity ZIL that we have here, which at the end of the day basically involves computing the logarithm of the density of the components, if we compute those logarithms and we subtract some constant, and this again can be any number, and then exponentiate and normalize, the result is the same as if we had started originally with the likelihoods or with the kernels, and we divide just by the sum. So why is this important? Well, I can pick b in any way that I want. Obviously, not every b is going to work equally well for the purpose of avoiding numerical issues. In particular, what we want is we want to pick a value of b that A doesn't produce neither an overflow nor an underflow in the computer, but also a value of b that just gives, at least for one of the quantities, a value that is reasonable. And a typical choice for that is just to pick b to be the largest value among the zik's that I'm working with. So it's typical to b as the maximum over L of the logarithms of the CILs. And if I do that, what should be clear is that one of these, so if I do that down here, one of these quantities is going to be exactly equal to 1. So for the L that corresponds to the maximum, I'm just going to be subtracting a number minus itself. So it's going to be the exponential of 0, which is 1. And for all the other numbers, because I'm using the maximum, I know that this is going to be less or equal than 0. So I'm going to be having numbers that are less than 1. And so that will provide some numerical stability. So let's look at how this works by using an example in the computer. We're going to illustrate the problem of computing the weights in a numerically stable manner in a mixture model by using a very simple example where we have two normal distributions. So it's going to be a mixture of two normal distributions where a priori we take the weights to be equal for both components. Those two components are going to have mean 0 and standard deviation 1 for the first one, and mean 1 and again a standard deviation of 1 for the second one. So we have a standard normal versus a normal that has a standard variance but is slightly shifted. And we're going to consider an observation x1 that is equal to 50. This is a little bit large for what you would typically observe if you had a mixture of this type, but this is just a small illustration. Similar examples can arise with less extreme observations when you have very high dimensional normals for your mixture components. So the observation is 50, and we want to compute what is the probability that that observation with value 50 comes from component 1, given that we know what the parameters of the mixture are. So if you think about how that looks like in terms of the formula, because the weights are the same for both components, they can cancel out. And at the end of the day, that probability is just equal to the density of a normal, a standard normal, evaluated at 50, divided by the same quantity plus the density of a normal now with mean 1 and standard deviation 1, again evaluated at 50. So this is the value of this probability in this particular little example that we're using. So let's see what happens when we run this through R. So let's first compute these two numbers, the two pieces that go into the probability. So if I execute these two commands, you can see down here how R is saying that this density evaluated at 50 is 0, and the same thing for the second density. Now, we know that these values are not exactly 0 because the density of the normal is strictly greater than 0 everywhere. In fact, the exact value, we have it here in the comments. So for the first quantity is a square root of 1 over 2 pi, multiplied by x, the exponential of minus 50 squared divided by 2. But because this number is relatively large, so it's minus 1,250, when you do the exponential of that very negative number, you just get a 0, and that's a problem with the numerical precision at which the computer can represent the number. So the number is so small that it's below the minimum that the computer can represent. So if you use these two values and then try to do the ratio, what you're going to get is an N, because in practice what you're trying to do is you're trying to divide 0 by 0. Again, this is a problem with the computer itself. It's not a problem that we have done anything wrong with computing our weights. It's just the fact that because the computer cannot represent these very small numbers, then it thinks that you are asking it to divide 0 by 0, when in reality that's not the case. Okay, so we discussed how to fix that, and the key trick is to do all the calculations in the log scale and then go from there. Let me correct a little mistake here. So what we want to do is we want to be able to do the computation in the logarithmic scale for the densities. And then if we add some value to the logarithms before taking the exponential and normalizing, then we have invariance in the result. And so this is just meaning to illustrate that if instead of having that very extreme value of 50, you use a less extreme value of 3 as your observation, and now you want to kind of compute the same quantity. This is a case where you can do it directly and you won't have a numerical issue. You will see that the probability is just 0.07, which makes sense because the mean of 0 is much farther away from 3 than the mean of 1 is to 3. So it makes more sense that the component with mean 1 generated the 3 than it is that the component with mean 0 does. So that is the value. And this is just to verify that what I did on the board is actually correct if you do it with numbers. So you can see that you get the same result in both cases for that probability. Now, how is that helpful in the case where x1 is 50? In that case, we cannot do this. So we cannot do the direct calculation here that is equivalent to this direct calculation here. So we can still use the second way to do it. And we're going to do it in such a way that we select this b not just in any random fashion, but we're going to select b as the largest of these two numbers computed in the log scale. Okay, so if we do that, we can see that now we get a very tiny number. We get essentially 3 to 10 to the minus 22. But the important thing is that we're not getting an n anymore. So it makes sense, again, that because the value is 50, component 2 is more likely to have generated the number than component 1. So this is consistent with our intuition. And we don't get a 0 number for the answer. Now, one thing to keep in mind is that it is important to do the calculation. So when we talk about computing in the log scale, it is very important that we do the calculation directly in the log scale. What that means is, for example, just doing the direct calculation of the d norm and then taking the log outside, it's not going to work. Let's do it here. So you can see that you get an n. And the reason is this number was already 0 because of the fact that you took that exponential of minus 1200. If you now take the logarithm of 0, what you get is minus infinity. So at the end of the day, what you're going to be doing is doing a minus infinity divided by minus infinity that is still undetermined, and that's why this doesn't work. This is just the same calculation of above, but instead of trying to do the d norm function, we're going to use directly the formula for the d norm, and you can see that again the problem is the same. You again get an n. On the other hand, if you use the d norm function in R with a log equal true, which is what we did above, this works. This just repeats a few of the lines that we had above. Or if you don't want to use the d norm function, the other thing that you can do is you can take essentially this formula up here, take the logarithm of that basically gets rid of this exponential and just works with the logarithm of this square root 2 pi. And that is also a correct way to do it, just a little bit more cumbersome in the context of R. But you can see that again gives you exactly the same result that you had above. So it's very important to remember to compute the weights or the pieces that go into the weight first in the log scale, and then do this operation of subtracting the maximum before doing the exponential and normalizing to obtain the probabilities. That's one thing to remember. But the other thing to remember is that doing the computation in the log scale does not only involve taking a log outside the d norm function as up here. That will typically won't be enough. You need to make sure that you are doing the calculation directly in the log scale by doing something like this or something like this.